future of stakeholders to identify optimization opportunities and make informed decision that prioritize sustainability and resources efficiency.
From design for 3D printing to material development, new process development.
Enhance precision, reduce timelines, enable complex design, fostering a greater collaboration across disciplines.
And I'm very happy to moderate this first session focusing on multi-material additive manufacturing. And we have a line of fantastic speakers from United States, Australia, and China. And it's a great pleasure to introduce the first speaker, Professor Banerjee. Professor Banerjee is a University Presidential and Professor and Regents Professor in the Department of Materials Science and Engineering at University of North Texas in the United States. He holds several appointments as adjunct and visiting professor in Materials Science and Engineering at the Ohio State University, Nanyang Technological University in Singapore, Indian Institute of Technology, Bombay, and Monash University. Professor Banerjee has over 350 publications in peer-reviewed journals and total citations exceeding 25,000. And today he's giving a talk entitled Additive Manufacturing of Compositionally and Functionally Graded Metallic Materials. Professor Banerjee.
Thank you very much, Paulo. So I'll start sharing my screen here. Okay, and go into the slideshow mode. I think everybody can see my screen, right? Yep. All right. Yeah, so thank you for the kind invitation, Paulo and you. This is indeed a very interesting concept. I applaud you for bringing this together as a webinar series jointly being hosted by the Singapore Center for 3D Printing at NTU, as well as the International Journal of Extreme Manufacturing. To my knowledge, this is the first of its kind in pretty much any field I have seen, so it's very unique and a nice concept. So thanks for the invitation. I am the first lead-off speaker for today, and I see that I'll be followed by Professor Milan Brandt as well as Professor Wang on different topics, but we are all focusing on sort of graded materials, graded metallic materials. I will focus my presentation on the more traditional way of graded materials, which is doing by directed energy deposition type techniques or blown powder processes in additive. Whereas I gather from the titles of Professor Brandt and Professor Huang that they'll talk more about the laser powder bed fusion side. So it should be a nice complementary set of topics to discuss on. So with that introduction, I'll just go through some quick acknowledgements. We started down this road many years back when, in fact, I was in my postdoc days with Hamish Fraser at Ohio State, when we purchased the first ever commercial lens unit. Many of you have probably heard of the lens technology, which is one of the directed energy deposition technologies, one of the first ones from Optomec, and in fact started playing with graded alloys, as I'll talk a little bit more in a bit. Then, of course, more recently, at least in the last 10 plus years, a very active collaboration on similar things with Raju Ramanujam at NTU, and Varun Chaudhary, who has now left and is a faculty member at Chalmers, and most recently with Paulo himself, who's hosting this. We are working on quite a few things, have a lot of plans for graded materials using AM. And a little bit, I would like to acknowledge Ruben Skaram for one of the topics I've decided to talk about today on functionally graded fracture fixation plates or bone plates, which is something I worked with him. He's at the University of Campinas or Unicamp in Brazil. And then a host of my former and current group members, I won't go into all their names, but they are at different places now around the world. And also the work continues with some of the recent students. So we are a group that has worked quite a bit on additive of titanium alloys, but also on other systems like high entropy alloys and some work on the nickel-based superalloy side and so on. And again, this is kind of just a generic motivation, probably known to most of you, that obviously the interest in metals additive manufacturing has been growing quite exponentially. In a way, I look at additive as the first wave was more on the polymers, plastic side, then the metal side has picked up in a big way, still very interesting and a lot of challenges, good maturity, but we have a long way to go. But one of the specific focus for today's talk is that with metals additive, you can do some interesting things in terms of compositionally or functionally controlling in a site-specific manner, in a single build or a single component. And that is a rather unique way to make materials, which is rather difficult with conventional processing. So what I'll do today is effectively talk about two examples so that we don't spend a lot of time on using directed energy deposition techniques, and I will just show you a little bit on that in the next slide. But we are talking about two examples. So the first one will be this concept of using graded alloys, or you might call it graded metallic multimaterials, to have site-specific properties for a specific application. And the example I'm going to take will be this modulus graded, or elastic modulus graded fracture fixation plate. It's kind of a real example which I found fascinating, as I said, with some of the collaborations we did with the group in Brazil and also others in the US. And then the second example will be a little different approach to using graded materials, where we use graded materials more in terms of a rapid assessment or a more combinatorial high throughput assessment of compositional space to figure out in a systematic manner what happens when we add a certain alloying element to a certain alloy to see how that changes the overall performance. And I've taken an example from more recent work on high entropy alloys that we do a lot of work using additive manufacturing too. And this is a magnetic high entropy alloy, aluminum, cobalt, and nickel, and effect of chromium additions to it. So with that, let me just delve into these two topics. So DED, I think most of you have heard of it. It's a blown powder process or directed energy deposition. We are not basically melting a bed of powders with a laser beam, but we are directly feeding the powders through a directed assembly system. So it goes through these powder hoppers. The powder hoppers deliver it through nozzles, as you can see here, and then the nozzles deliver the powders to the location where the laser beam is hitting a substrate. So you are effectively melting the powders that are kind of blown into the localized melt pool on the substrate. And then you raster, you could have multiple systems. So the simplest one is rastering in the XY direction the substrate and the laser head along the Z axis. And that way you can build layer by layer. The feeding is usually coaxial of these powders. There are different technologies for powder feeding. I'm not getting into that. Cooling rates are usually, I would say, in the range of 10 to the power 3. 10 to the power 5 is actually very difficult to achieve unless you have a very high conductivity substrate or cool water cooling or so on. But it is in the lower end of cooling, but still you might say rapid solidification type situation, but not as in laser powder bed fusion, where you can get up to 10 to the power 5, 6 quite easily, Kelvin per second. A larger beam size allows you to go for larger printing of larger components, of course at the cost of surface finish, but you can also get faster build rates with this compared to laser powder bed fusion. And it's a very good technique for compositionally graded alloys. As you can see, these different powder feeders allow you to control the feed rates from individual feeders, and you can build different types of gradients. A simple one like this is just a gradient from one composition to another in any geometry you like. We tried these types of simple geometries for a long time, even for assessing what the effect of composition is, or as I will show you, for site-specific properties. Just to reiterate, I mean, if you build like digitized steps in a compositionally graded alloys using a DED type of process, you can then do a lot of things subsequently. You can actually heat treat them. You can do even mechanical working if you want on this material, like forging or rolling, depending on what your intention is to, if you introduce thermomechanical processing into it. You can do the measurements of composition with along the gradient, microstructure. It allows you a lot of different things to do in a single small range of a build. But you can even get mechanical properties like microhardness and modulus and so on. And as I'll show you in the second part of my talk, an example of magnetic properties, looking at those as a function of composition. Some of the initial work we did goes back to like early 2000s, as you will see, when I think this was the first set of DED processed metallic alloys that we started publishing on. Work started in late 90s, 98, 99 on the first lens systems back at Ohio State when we were looking at it. So let's go into the two examples. The first one, as I say, was this graded metallic multimaterials with site-specific properties for a fracture fixation plate, which I'll explain to you in a minute. It's like a bone plate, and why that can be quite important in terms of achieving the required set of properties in a site-specific manner. So just to give an example for those of you, the internal fracture fixation surgery is something that an orthopedic surgeon often does, tens of them even in a single day. This is a very common surgery. It's related to what you would call as kind of a catastrophic fracture in a big bone of the body. Say, in this case, I'm showing you an example of the femur, which is basically this bone here. You can have a fracture from whether it's an accident or some other reason, and say the fracture is in a location like this. And it has effectively, it's not like a hairline crack. These are situations when you have a fracture where the two parts of the bone have completely severed or separated from each other and got displaced. Now, what the orthopedic surgeon would typically do is to use this bone plate, and then which has holes in it, and then drill holes into the bone and hold this two pieces together. This is a classic. These are often made of stainless steel. This is how a typical bone plate would look. I'm giving you examples of real bone plates from what almost looks like a carpenter's toolkit, but I can assure you this is actually what the orthopedic surgeon's toolkit looks like, and they use this all the time for these fractures fixation surgeries. Now, there are some challenges with this. First of all, the bone plates of stainless steel or titanium that even if you use, they are much higher in modulus. Let me show you the second table. So if you take stainless steel, the elastic modulus of stainless steel is 200 odd. Cobalt, chromium, moly, 200, 230. Even titanium or Ti64 are in 100, 110 range. All of these are way, way higher than the typical 10 to 40 GPa, more like 10 to 20 GPa, which is the elastic modulus of bone. This results in a modulus incompatibility that leads to an effect called stress shielding. And this is something, again, this is a mechanics concept. I can go into it in more detail, but in the interest of time, I will just leave it for now. So what you want is a better compatibility between the metallic implant and the elastic modulus of the bone. So you need newer alloys. Number two is the biocompatibility of these types of materials. So Ti64, which is the most common one, over the years, there's been some concerns over cytotoxicity due to aluminum and possibly a long-term, cytotoxicity from vanadium, and aluminum can have some long-term neurological effects, including Alzheimer's. These are not very well established, but again, Ti64 is still used very widely, but there may be better options to use some of the, I would call it more BCC stabilizing elements or beta stabilizing elements like niobium, zirconium, tantalum, molybdenum, which are also been shown to have better biocompatibility. And then again, there is inadequate wear resistance and so on that we have to worry about. So this is on the material side. But there's a challenge in terms of the design also of a fracture fixation plate. So if you think of this fracture fixation plate, which you see here, one of the things you will notice is that this is, if it's got a constant modulus all the way through, then the region of the fracture, you are effectively nicely shielding. But far away from the fracture too, the bone, in the regions where the bone is healthy and there is no fracture, you're still shielding the stress from there. So this results in the classic stress shielding and can lead to osteoporosis or reduction in bone thicknesses in these regions. And that's a big challenge. So how do we kind of get over this while we want to shield the fracture from stresses, but not the regions away from the fracture? And this can, so one of the ideas we proposed is that can we use a fracture fixation or bone plate where the elastic modulus is graded? Now, when we looked at the literature, there were suggestions like that from the mechanics community. This is from the Journal of Mechanics for Biomedical Materials back in 2012. They suggested having a thicker section near the fracture and thinner. That will obviously give you. But But the orthopedic surgeon, this is not a great design because your cross-section thickness is changing and it doesn't sit flat on the bone. So there are challenges in that design. So is there a way to have a constant thickness but an actual change in modulus? This is what we designed with the change in local composition and a graded alloy. And what we did is it's a very simple proof of concept example. This has not been developed in the form of an actual design, but the proof of concept was there that if you remember, I didn't talk about these alloys earlier. There are some low modulus alloys that have recently been developed, which a lot of niobium and zirconium and tantalum type elements, which can reduce the modulus of Ti64 to almost half of it, so about 50, 55 GPa, much closer to the bone modulus. So if you use one of those alloys and make that towards the edges, which is the low modulus, and we grade with composition the modulus. So this is the composition gradient across this build. The build is relatively tall. This is made by lens or DED process, about 55 millimeters tall, so more than 2 inches. And you can see that it is 13 millimeter by 30 millimeter cross section. So actually this is the initial build, and then we machined it. But you can see the composition steps are given here. So in the center you have CP titanium, which is the high modulus titanium alloy. High modulus of titanium you have like 110 GPa. But on the other side, as you go further, you would expect the modulus to go down because of this alloying with other elements. So based on that, then you can look at the X-ray diffraction from each of the layers. Here we decided to do 5 macroscopic layers. They're very thick. In a real design, you would like to make them much thinner, but this was just a proof of concept, as I said. And you can see the distinct differences in the phases present. Again, I'll just quickly go through them. So you had some beta plus alpha plus this BCC niobium was unmelted niobium. So powders, this is what gave rise to these peaks. And they happen to occur when you had the highest niobium. So there's no surprises there. But bottom line, you got the BCC phase, some alpha phase coming in, and the fraction of alpha phase, which is the HCP phase, increases as you go to CP titanium. CP titanium, by the way, is going to be 100% alpha because there is no BCC stabilizing element in that. So, but the corresponding change in modulus, which we measured with 2 independent techniques, this is from the ultrasonic measurements. So at the edges, the modulus is going down to the range of 75, and this is using ultrasonic, so I'm about 72, 73 to 80. If you look at it from an instrumented indentation, again, it's pretty similar, 70 GPa, whereas at the center, the values are as high as 110, 115 GPa. And this is nicely grading on both sides. It's a symmetrical gradient as you would want for an actual fracture fixation plate, with the central region being nicely shielded, shielding the fracture side, but the edges have lower modulus. So this worked as we wanted to design it, and it is the design of the modulus. In terms of the hardness gradient, it was not as much, which is fine because we really are, the mechanical strength of all these alloys is reasonably high for the purposes that we need. So it should be fine. The hardnesses were lying in the range of about 250 plus 270 to 350, which is fine for the application intended. So this is the summary, and on the side here, I wanted to show you that this original build was then further machined. So we showed the proof of concept that we were able to drill these holes into these layers, maintain the mechanical integrity, and it was also mechanically finished or polished to form exactly like a fracture fixation plate would look like with this modulus gradient. So this is one example I wanted to show you of how you use a compositionally graded alloy with a site-specific change in property. In this case, the elastic modulus is what we were grading to get this nice graded fracture fixation plate, which potentially could be used in actual surgeries. So the second question, the second example I'll give you, as I said, was a different approach. This is not to necessarily create a particular component, but to use the concept of graded metallic multimaterials for high throughput assessment of a range of alloy space compositionally. And the example I'm going to give you is a recent case we looked at where we take one of these high entropy alloys. This is an aluminum, cobalt, iron, nickel type system, which is a very soft, magnetically soft high entropy alloy, but when we add chromium to it. And the rationale behind that I will just explain to you in the next slide. So to give you a little bit of an introduction, so that in interest of those of you may not be aware with the system, this is a common type of high entropy alloy. I mean, this is similar to a lot of these 3D transition element based high entropy alloys. But what we were looking at specifically is, can we design that something where I can tune the magnetic properties and the mechanical properties at the same time? To do that, we are using this approach of graded alloys to screen, you might say, or see systematically what happens with a change in composition. Now, why select this composition? Well, cobalt and nickel are three of the strongest ferromagnets in the periodic table. So COFeNi is a very good, what you call ferromagnetic system. Addition of aluminum promotes a BCC phase formation in this and actually makes a B2 ordered phase. So this B2 ordered soft magnetic phase is the starting point. It has good properties from a magnetism point of view. However, we are trying to see that can we tailor the magnetic properties and the mechanical properties by adding chromium. Now, why are we choosing chromium? Well, what does chromium do? Well, first of all, chromium is a strongly antiferromagnetic element. So by adding chromium and replacing cobalt, you're going to change the magnetic characteristic of behavior, which I'll show you in a minute. But also there are other changes chromium does. Chromium introduces a miscibility gap, as you will see in this. This is basically an isoplet, like a pseudo-binary phase diagram. So on the left here is the AlCOFeNi composition, this composition, and I'm adding chromium and replacing the cobalt. So we basically, what we do is we increase increasing chromium and reduce the cobalt. You see it opens up from this BCC. This is the BCC B2 region, which is actually B2. This is the way thermocalc labels it. It's a single B2 phase here, but then it opens up this B2 plus BCC region. So it's opening up a miscibility gap by adding chromium, because there's a tendency for phase separation or spinodal decomposition that chromium does to this alloy system, especially with elements like iron. So then the idea was, what are these going to do in terms of the magnetic behavior and the mechanical properties? Can it help us design for a certain range of properties that we are interested in? So this is the results from it. Again, we go from AlCOFeNi with no chromium to 100% chromium replacing cobalt, which is Al chromium and nickel, over a range of 1, 2, 3, 4, 5, 6 steps. So you can see here, these are the respective compositions. If you look at it from an XRD point of view, you can clearly see all of them have fundamentally BCC peaks. But if you look carefully, you can see these superlattice reflections arising, and these reflections are not very clear here, but if you zoom in, you can see them. These are the superlattice reflections from ordering in the BCC phase. So there is a B2 phase also forming in this system. And otherwise, it's pretty similar. You don't see a huge change, but this is only at the XRD level. If you interrogate it using more advanced microscopy, what you see here is that the first region, which is no chromium, pure cobalt, it's almost equiatomic AlCOFeNi. By the way, I must re-emphasize here that we are using blended elemental powders for making them. So the compositions are not exactly dead on. There are some changes from the exact equiatomic, but this is using elemental aluminum, cobalt, chromium, and nickel. So here there is no chromium. You can see this is pretty much B2, as the electron diffraction pattern shows you. They look like large grains of a single phase. No surprises there. However, we also do some very advanced analysis using atom probe tomography, and this is what I'm showing you here. So in the atom probe tomography, we saw that compositionally, it may not be perfectly uniform. There are regions, or you might say compositional fluctuations, very small changes, but enough for the atom probe to statistically find out that there are regions that are richer in nickel and aluminum and regions that are richer in iron and cobalt. So it's like there's a very early stage of a phase separation, but largely it is a single B2 phase. Now, when you go to the replacement of about 5% chromium addition, so you see the total amount of cobalt plus chromium remains the same, you would now have nominally about 5% chromium and about 20% cobalt. As soon as you do that, you can see there's a change. You can see that there is a, when you do the dark field TEM, I'm not getting into the microscopy details, but you have a two-phase mixture more pronounced. And this is a B2 plus BCC type of mixture. I'll show you that in the atom probe data also. So it's not uniform B2. And at the grain boundary, even in the SEM, you see a second phase forming, which is an FCC-like phase. Now, mind you, I did not point this out to you earlier, but the prediction shows this little region here that if you add some chromium, okay, small amount of chromium, you start forming an FCC type phase field here. This was from the prediction even from thermodynamics or thermocalc. So this is definitely happening. But this actual microstructure at a higher resolution in the atom probe is very interesting. You have BCC precipitates that are forming within a B2 matrix. All the compositional details are given here. Again, I'm not trying to just focus on the microstructure, but this has some significant impact on the magnetic properties, which I'll get to in a minute. But what we are seeing here is that you have fine-scale BCC precipitates that are rich in chromium, and they're actually rich in iron and chromium. And in a matrix of nickel, aluminum, cobalt, which is the B2 phase, the ordered B2 phase. So it's a two-phase mixture. And these discrete precipitates are forming due to the addition of the chromium, is the point I wanted to highlight. And you can see that very clearly. They also have a core shell structure and so on. Very interesting microstructure, not just from a structure point of view, but also magnetism. And I'll get to the magnetism in a minute. So now I'm going to the case when I add more chromium. So now we are having, if not equal chromium and cobalt, but almost there, 15% chromium, about 12-13% cobalt. This microstructure is completely different now. You have a what we would call as a spinodally decomposed microstructure, because this type of these images show you a two-dimensional section through a three-dimensional co-continuous mixture, which is, and this mixture is of nickel aluminum rich regions and iron chromium rich regions, right? And also nickel aluminum cobalt rich regions and iron chromium. This is a classic spinodally decomposed microstructure. So that again has changed. And this goes back to the idea that as you're increasing the chromium content, you increase the tendency for phase separation. The system no longer wants to be a single B2 or BCC phase. It wants to split up into two phases. The atom probe data again is very clear on this. The BCC phase, as you can see here, I'll just highlight the compositions. It's a little small here, but you can see that BCC is heavily enriched in iron and chromium, whereas the B2 phase has got significant amount of nickel and aluminum, but also quite a bit of iron and cobalt is still retained in there. So this is the nature. And all this gives you some very interesting insights into how the phase decomposition behavior takes place. Again, all within, in this case, like a 1-inch size block of material that you made with the DED process. Finally, this is just the same thing. When you have no cobalt, complete replacement of cobalt with chromium, almost 25% chromium, you have a much coarser decomposed spinodal structure, very nicely divided up into B2 and BCC. Again, you can see the length scale is higher. This is a 500 nanometer length scale. So you're talking of decomposition patterns in the 100 nanometer scale now. Again, the trend in the atom probe is the same. You have a nickel aluminum rich B2 phase with some amount of iron, and the iron and chromium pretty much forms the BCC phase. So finally, what does this do, these changes, in terms of the magnetic behavior, which is what we were really trying to understand. So if you look at it, it's a very interesting magnetic behavior. Yes, if you look at the blue curve, which is our saturation magnetization, there are no surprises there. If you look from the left corresponds, actually, let's start from the right. The right corresponds to the region which has pure aluminum, cobalt, iron, nickel. The high amount of ferromagnetic elements, cobalt, iron, nickel, means that the saturation magnetization is high. As I told you right in the beginning, chromium is an antiferromagnetic element. So as I keep adding chromium, that is going from right to left, the saturation magnetization is very nicely systematically decreasing. You have a large range. I mean, you have close to 140 or 130 Gauss, not Gauss, the EMU per gram MS saturation magnetization. You're going down to 20 by 6 times less. So this is systematic, and you would expect as you replace cobalt with chromium, you are going to go to lower and lower saturation magnetization. What is not expected is the trend in the coercivity. On the, again, this very soft behavior of AL, CO, Fe, and I, very low value of coercivity, less than 10 oersted or so. But as you keep adding chromium, it increases. You can clearly see an increase. And this is when that phase separation takes place. If you remember, when you added chromium, you started forming initially iron chromium rich precipitates and then into a spinodally decomposed microstructure. But it reaches a peak value. Again, the peak value is going from about 10 to 140, it's 14, 15 times higher. So this is, forget being soft, this is definitely semi-hard magnetic material getting close to being more harder. But suddenly, again, it falls down. Even though this is decomposed spinodally, as I showed you the evidence of that microstructurally. So it's a very interesting interplay of the magnetism with the microstructure. We still haven't fully resolved this, but we have some ideas about the scale, the length scale of the decomposition, and how that could be influencing the coercivity, because the change in coercivity is definitely non-monotonic as you change the chromium content or replace more cobalt with chromium. So that is, yeah, this is just a summary what I told you. This is the part that is very interesting and came out of this high throughput combinatorial assessment using compositionally graded alloy made with DED. So the summary of this part, just the second part of it, is again, the DED process was used for making a graded HEA. And why? Because we were trying to look at how can we look at the interplay of the compositional change with chromium addition to cobalt in the high entropy alloy to the magnetic properties. So in the very early stages of phase separation were observed in this ALCO FENI case, but magnetism wise, it was really nice because very low coercivity, high saturation magnetization. But as we add increasing chromium, your saturation magnetization came down, but it is what happened is the coercivity had a different behavior, and these are the reasons for it. So when you add chromium, you first form these BCC precipitates, which are iron chromium rich, and that in fact will still reduce the coercivity, it's reduce the saturation magnetization, but increase the coercivity because you are introducing these precipitates which can be barrier to the magnetic domain wall motion. And eventually, though, what's happening is that increasing chromium pushes it into more and more of a phase separated spinodally decomposed microstructure, and it becomes coarser. As it becomes coarser, you're reaching a point where the spinodally decomposed microstructure is not as much of a barrier because the magnetic domain walls can move within each of the B2 and BCC phases and still again become softer in behavior, which is what the lower coercivity appears to be doing. So again, this is an example of this assessment that we could do with a DED processed compositionally graded alloy. It might have been very difficult to do if we literally had to look at every single alloy made separately by conventional processing like arc melting. So with that, I hope I could give you two examples of the way you can use these compositionally graded materials. I think it opens up a very, very important frontier in terms of materials processing, and definitely in the domain of extreme manufacturing of materials. Thank you very much.
Thank you very much, Professor Banerjee. We are now open to questions. Yeah, we have the first one.
Yes, I can read it in the chat box. That's the one, right,
Okay.
Paulo?
Yes.
Yeah. Yeah. So, okay, the stress shielding. So, in terms of stress shielding, if I understand your question, are you talking about the management as in the reduced modulus, or what stress shielding is? Either way, I just want to clarify the question. Should I explain the stress shielding angle a bit better, or probably
No,
that's what?
I believe that the question is considering the aspect of the equivalent elastic modulus and yeah,
Right.
to avoid
Yes.
the
So
problem.
yeah, let me see. I can quickly go back to that slide in a minute. Yeah, let me just keep it in this mode to be faster. So if you look at so the idea is that if you look at the modulus, the stress shielding takes place because eventually with the bone plate you're still going to load the bone. This is during regular, this is just a simple cartoon, but what it shows is you walk or you run, you're going to be keeping loading and unloading the bone plate and the bone. You want the distribution of the load to be such that as closely as possible the bone and the bone plate have a similar level of stress. However, if the modulus of the bone plate is very high locally, then that will bear more of the stress for an equistrain condition from a pure mechanics point of view. So automatically what happens is the bone plate starts taking more of the load, less is taken by the bone, and then the bone is a living tissue. So effectively, it results in the bone over a long period of time shrinking because the body thinks the role of the bone is defunct because most of the load is taken by the bone plate, which is a static inert material. Right? So that is the idea, that if I can reduce this here, then the less stress shielding takes place in the healthy part of the bone. Whereas in the fracture side, it's not necessarily the case. You don't want the bone to see a lot of loading. So you in fact want the bone to see less loading, and you want it to get more time to heal, whereas the bone plate can take most of the load when the physical activity of walking running, what the person is going on. So that, I hope that's a little clearer, or if you want any more clarifications, let me know.
Any other questions for Prof. Banerjee? This is really a very hot topic. So the use of 3D printing for the fabrication of multi-material functional graded structures. In your opinion, what are the major challenges?
So I think that the challenges to me are, first of all, again, there are different processes. There is using the DED, the technique was probably of making graded alloys has been established before powder bed fusion. But as we will hear from Milan and also Professor Wang, there is more recent developments in that area which we are not directly working on, but it can be done. The advantage with the laser powder bed fusion, for example, would be the ability to do much finer surface finish and also much finer layers, right? So that could be helpful, because one of the challenges I think for a real application is that for a graded material, you need to know what is what I call the grading length scale, okay, at the interface. The interfaces become very important. If you're going to just have a digital interface from A to B material, usually from a mechanical behavior point of view, or even from other things, think of corrosion, electrochemical behavior point of view, those are not good interfaces. Now, naturally, when I am using a process like additive, you really don't get atomistic level interface. You are going to get some compositional diffuseness. But what is the level of that compositional diffuseness do we need in order to get to the point of a homogeneously distributed load across the different layers across the compositional gradient? Or it could be, if it's not a loading application, we don't form a very diverse electrochemical couple. I'm just taking two examples, Paulo, like corrosion and mechanical behavior. But there are so that interface has become the very key role. So I think there are many more questions coming in. I just saw.
Yes, several questions are coming. So let's start with this. Behind the two examples, what other material systems or industrial applications do you see as most promising for lens fabricated compositional graded metals, and what barriers might hinder their adoption?
Right. So yes, so I think that the points that have been already mentioned in the question are definitely big ones. That is, the cost and the scalability are two of the barriers. And as I also said, that in graded materials, what I was just mentioning to you, Paulo, the interfaces are very critical. So how are we designing the interfaces? What is the length scale over which a gradient? Supposing I have got change from composition A to B, how close do A and B need to be so that my material works well? Take a simple example. We designed this fracture fixation plate. We have not really put it into use, but one thing we have not done at all is, for example, fatigue loading. In a real biomedical system, you will need to look at the fatigue behavior, and fatigue can be very challenging when you have different moduli in different regions of the the same implant. So can we design that better? Those are the types of things that will come up and can be, so it's very promising, but I still think there's a long way to go in terms of actually applying them in an industrially acceptable manner. That's very important, I think so.
You highlighted the coupling of compositional gradation with unconventional additive manufacturing thermokinetics as a complicating factor. Are there specific strategies to mitigate this complexity and improve microstructural control?
Yes, so there are two things that we found. The first thing is, the most standard way is you build the compositionally graded material, but then follow up with post-processing heat treatment or thermomechanical processing. Once you do that, especially heat treatments, without distorting the shape, of course, you have to be careful. But if you do a heat treatment, you can go back to a more homogenized microstructure, which will, you might say, obviate or remove the effects from the thermokinetics. So yes, the thermokinetics will play a role, especially if you're building something from a substrate. We have to be aware that not only are you changing the composition, you're also changing the thermokinetics as you go further away from the substrate. This is the simple heating cooling cycles. So if you want to remove that effect, and you can go post-process heat treatment. The other way, more complicated but doable, is that not only change the composition, but also change the process parameters when you're changing from one composition to another, which can also be programmed in to try to get back to the similar thermokinetics in each layer. It's not easy, but it is possible. Yeah. So those are the two approaches that we done. Yeah.
In the high throughput development of magnetic high entropy alloys, how does direct energy deposition process ensures compositional accuracy across the gradient, and how do you validate the uniformity of composition versus property relationship in such combinatorial samples?
Yes. So this is a very relevant question. As I mentioned, if I can get a pre-alloyed powder, it is always preferable over using blended elemental approach. However, when you have these complex compositions, it is very difficult to get pre-alloyed powders. It could be the powder processing itself is difficult or prohibitively expensive. So using elemental blends or blended elemental approach is often the only way out. What we have done over a long period of time, at least with DED, is that we calibrate our powder feeders for the specific system in advance for each types of powder, elemental powders we're using, and get to the closest composition. However, despite that, as I showed you in the case of the ALCO FENI, I mean, just to give an example, I'm just picking on one. If you see, this is a case where, we had more aluminum than we wanted. We had lower chromium. So our logic is simple. We may not exactly hit the composition we intended, but we measure the composition that we actually got very carefully with techniques like EDS and even all the way up to atom probe if necessary. And then use that composition that we measure to correlate with the microstructure. So that gives us at least a foolproof correlation. Now, are we achieving exactly the composition in every single layer? No, not always. But within, I would say, a few percentage, you can definitely do it. Yeah.
Yeah.
If you carefully do it. Yeah.
We have time for one final question. There are several questions.
I know there are several coming up.
I
let you choose, Paul.
all the viewers to send additional questions to Prof. Banerjee. But the final question, and this is related also to the orthopedic plates. So for the functional graded orthopedic plates with engineered elastic modulus gradient, what into actual mechanical performance during the lens process?
Right. So yes, I think that both this question and the second question, I mean, the related question that is there on the unexpected interfacial issues are very relevant. As I already pointed out, we did not observe any unexpected interfacial issues because one common thing that comes up in such compositions or such graded layers is that you can form unwanted intermetallic phases like embrittling phases. You may go from composition A to B, but in the gradient, again, if you look at the choice of our elements, that's one thing we did. If you see where I'll just take this as you see, go from titanium, you're adding niobium zirconium to reduce the modulus, but none of this system does not have a tendency to form an intermetallic compound that can be embrittling. If, for example, I had added chromium or iron, which are also very good BCC stabilizers and can reduce the modulus, I would definitely encounter phases as far as possible. So that's one thing to keep in mind. The other problem, which I already mentioned, is that the modulus gradient looks great, hardness looks great, but I have no idea of the fatigue behavior. And that's one thing that is going to come up in a real engineering design, especially for a fracture fixation plate, because even this simple cartoon shows you this is a fatigue loading. So we have not gone into the biofatigue approaches. So we have not translated it. So please don't get the impression we have translated into a real component. What I wanted to show you is a proof of concept of this type of approach. But I think with sufficient design criteria being fulfilled and a more subtle, not the kind of example I'm showing you here, this is just I would call a too abrupt change. You want a much more subtle variation in the modulus, which can be done. This is just a proof of concept. You should be able to get to more smooth fatigue behavior across the layers. So that's my answer.
Thank you very much, Professor Banerjee, for such an excellent presentation. And again, I would like to invite all the participants to send additional questions or to us or directly to Professor Banerjee.
Yes, and you can, if you can collect it, Paulo, they can just send it to me by email. I'll be happy to answer to you. Yeah.
Thank you very much.
Thank you.
Now it's a great pleasure also to introduce the next speaker, Professor Milan Brandt. Professor Brandt is a distinguished professor at RMIT in Australia and the founding director of the Center for Additive Manufacturing. Professor Milan Brandt is a globally renowned leader in advanced manufacturing and received several awards, such as the 2020 Laser Institute of America Highest Award and the Harter Shallow Award. He published more than 360 high-impact publications that received over 90,000 citations. Professor Milan Brandt is going to introduce the additive manufacturing activities at the Center for Additive Manufacturing, followed by another presentation from Dr. José Lozares, a member of the center, that will talk about multi-material additive manufacturing with laser powder bed fusion towards functionally graded components. Professor Milan Brandt. Professor Brandt?
I'm here, Paolo, but thank you very much, Paolo. Okay, and hello everybody. I'll share my my presentation. So, in the interest of time, I might skip some of these slides, Paolo. But maybe just a quick one. I wanted to basically tell the audience a little bit about our advanced manufacturing precinct and the Center for Additive Manufacturing, and some of the work that we are doing in this area. And then we'll have one of our PhD students who's in his final year, José Lozares, give a presentation on his PhD topic involving laser powder bed fusion. For those not familiar with RMIT, it's based in Victoria, in Melbourne. Melbourne is a large city, 5.5 million people. It's a modern city. RMIT itself, it's an old institution by Australian standards. It's 124 years old. And it has always been in manufacturing. And we are also a dual sector university, so we have both higher education and vocational education. And we currently have something like 100,000 students in Melbourne. We also have campuses in Vietnam and Singapore. In terms of our additive manufacturing journey, we really started in 2010. We were one of the first universities to get into additive manufacturing because of globalization that was taking place. A lot of our industry and manufacturing was going offshore, and university wanted to stay in manufacturing, and they basically decided to work in additive manufacturing as this was rising globally. In 2020, things are sort of changing after COVID. So the driver for additive manufacturing, not just at RMIT, but other universities and companies, is sovereign capability, which is really offered by additive manufacturing. So in university set up this advanced manufacturing precinct in 2010. It's a $30 million research and teaching facility. It's unique in Australia. It covers both metal and polymer-based technologies together with high-end CNC machines. So we are sort of promoting ourselves as a one-stop shop for industry in terms of research capability. And these are some of our equipment. So we've got a range of polymer systems, large FDM machines. We've got Mark-forged FX10 printers. For our teaching, we use bamboo printers, so 30 plus printers. And then there's a PolyJet 750 and an SLA machine. In terms of our metal machines, we've got 5 powder bed systems. The largest one is SLM Solutions 500. It's a quad system. We also have an Aconity MIDI Plus we've been working with for the last year and a half. And that's a very fancy research machine. If you're not aware of it, it comes with N-Light laser, and you can vary the beam profiles. It comes with a whole heap of sensors. So we are also looking at AI. Basically, we extract a lot of data and look at process monitoring, process control. We've got a large trump system on bottom right of the slide. with a range of thermal sensors, and that's where we do a lot of our multi-material research. And on the left-hand side of the slide, we've got a WAM machine for really high metal deposition. And we're also looking at some projects involving multi-material with a WAM system. This is all supported by high-end CNC machining centers, scanners, and all the usual things that come together with additive manufacturing. We also have a concrete facility. It's not based within AMP, it's another part of the university. There's quite a bit of work going on in this area in terms of new materials for printing houses and other sort of civil structures. In terms of the centre, we're fairly large. There's something like 17 academic members. We usually get something like 4 visiting professors on a regular basis, 16 full-time researchers, and sort of 30 plus PhD students. And we've graduated over 100 PhD students since 2010. Our budget, our income, I should say, is about 5 million. This is research income per year. And we certainly publish over 100 publications per year in high-impact journals. The areas we're focusing on at the moment is sustainability, application and materials development, so machine learning and AI, technology and process development, and surface technologies and post-processing. And as I mentioned, we publish in high-impact journals, so we've had 4 Nature papers in the last four years. And these are sort of some of our firsts. So in the top left-hand side, we 3D printed a lattice-based spinal disc that was implanted into a patient in 2015. We've got a couple of satellites flying, and they were launched in 2019, 2020. And we've done quite a bit of work with sort of animals and 3D printing their implants. And, we really interact with many companies locally and globally. And also, if there's any interest from the audience, we're certainly happy to explore possibly collaboration, future collaboration. Now, in terms of multi-material, and Professor Banerjee gave a detailed explanation of the sort of the DED process where you're injecting metal powder, and you can obviously mix a number of powders together to create graded structures. The other process is laser powder bed system shown here, where you pre-place a layer of powder, and powder particle size typically sort of 20 to 60 microns. And then you run a laser beam over it based on the CAD file. And then the platform descends by the layer thickness, and the layer thickness are typically 30 microns. And then another layer of powder is pre-placed, and then the process is repeated. So most of the work in this area up to recently has been done with single alloys, but there's quite a bit of interest in basically working with multi-materials. The challenge there is the technology. It's not as simple as the DED technology in terms of multi-material processing. And there is quite a, in terms of LDD, I mean, Professor Banerjee has published a review article a couple of years ago, and it basically shows you the sort of the range of materials and the multi-materials that have been published over the years, and you're really talking about 25, 30 years. So this technology has been around for quite a while. One of the challenges, I guess, and that Professor Banerjee didn't mention, is the certification. So if you're talking about aerospace components and even medical implants, it's a certification of this graded structure. So that's certainly one of the challenges that's been faced by industry as opposed to sort of monolithic materials. Oops. So these are some of the Here's the sound. So these are some of the examples of our DD where we use multi materials for a repair application. These are aerospace parts. We've done some internal cladding. We're mixing 420 stainless steel together with 4140 steel to produce certain microstructures with certain hardness and fatigue properties. There's another example here of again aerospace type components where it shows wear damage, which then we machine the wear damage and deposit a mixture of 420 and stainless steel plus 17.4 pH on a 13.8 pH substrate. We had to get certain hardness as defined by our Department of Defense. Now, in terms of laser powder bed fusion materials, as I mentioned, there are a number of approaches. These are shown here. This approach in A involves a system where you have two different powder materials, and then you, as the recoater goes over the substrate, it deposits one. Then you can run the laser beam, and then as the recoater comes back, you can run another one. This approach here uses ultrasonic powder dispenser. This is Professor Lin Lee's work in Manchester when he was at Manchester University. Then the work done by Conity. You've got these drums where you have powder on the surface, and then the powder dispensed across the powder bed system. And then there's a combination of these different techniques. So in terms of TRL level with these technologies, it's really 1 to maybe 2, depending on the technology that you're working with. So it's really very, very early days, but there are lots of opportunities in terms of the microstructures and properties that you can get using this technology. And this is a little video from Conity. So our system has 2 cylinders, and we can do 2 materials, basically. And as Jose will show you shortly, this is some of the work that he's been looking at. So I think on that note, I'll hand over to Jose. Thank you very much. Paolo, I don't know if there's any questions, happy to answer, or...
I think that we'll have the questions at the end, Milan. Jose, please.
Can you see all my screen?
Yes.
Perfect. So, well, thank you very much, Milan, for the sweet introduction. So I'm Jose. I'm a digital student at RMIT University, but also at Hamburg University of Technology at ISM Group. And today I will bring some of the latest results and insights from my thesis, my talk on multi-material AM with laser powder bed fusion toward functionally graded components. So here's a brief overview of the contents that I will cover during the presentation, which opens with a quick introduction and motivation section, a brief explanation of what is multi-material PBF, mostly the benefits. I will go over the challenges and the current status of the technology, and then I will introduce some of my recent work. So if you think of let's go for the motivation a little bit. So if you think of one of the biggest marvels in engineering, you might think about the Starship rockets from SpaceX, right? So space and space industry are playing fields that could answer to many research questions from many disciplines, but we cannot get there the way we do now. We need to be more efficient, make a better use of our resources, and all that without skyrocketing the bill, which is already around 90 million per rocket, according to the latest report, I believe. So I made myself the question, how can we make this thing cheaper? Well, if we look at the metal components manufactured through additive manufacturing in this rocket, we can find the combustion chamber, which is inside one of these 34 cone-shaped parts at the bottom of the rocket. So combustion chambers are one representative component from this space launcher market that receives this level of attention because the need of high cost effectiveness. In summary, this chamber is in charge of providing a volume for combustion and converting the thermal energy into kinetic energy. For liquid rocket engines, temperature control of the thrust chamber or the combustion chamber is fundamental to secure that the correct operation of the engine. And to achieve this, one interesting approach was covered by NASA, and it's still covered by NASA, and is the use of a multi-material chamber. So the multi-material components are very interesting alternative to monolithic or single material components thanks to the combined properties of two different metal alloys. For example, heat dissipation from a copper-based alloy and structural integrity from a nickel-based superalloy. Thanks to recent advances in additive manufacturing, particularly in powder bed fusion, now new systems allow us to control the distribution of each alloy within the 3 dimensions, including the distribution within the layer too. So these advances shed light onto the game-changing potential for the development of finer, more intricate multi-material regions as a direct AM competitor, which is DED, which is the only, I would say, is the main principled multi-material technology able to create multi-material parts, is a bit restricted on the resolution that we can achieve because of the nature of the process. So what is multi-material PBF? So multi-material PBF is just a small branch, or small branch. So far, we could get bigger. A new branch of the well-renowned powder bed fusion process with a small update. It allows us for the deposition within the same layer. This allows us, again, as I said, having transitions of materials not only in the building direction, but also within the same layer. Among the main benefits from multi-material, we've already listed the unification of material, feedstock size, overall lead time reduction, one thermal history, less production steps, tailored properties, reduction of total parts. These we are all very familiar with, but if you go for PBF, you can also benefit from better mechanical properties, a higher cooling rate, and a smaller notebook size that you can control, high-end resolution, and let's say less post-processing because we are not going to get rid of it in any of the AM technologies, but definitely less. So researchers on multi-material worldwide can benefit from the previous assets and can generate new lines of research, which briefly I will mention some of the insights that we got from APICAN last week. Some of them were improved performance with functional regions, which you can find in the example I just described with the combustion chamber. Metamaterials, for example, with auxectic properties that we were seeing some last week, and also property tailor and microstructure control. So if the technology is looking so nice, why is it not taking off? Well, some of the technical challenges can be classified in the categories that I've described in this slide. So the first one is that material arrangement of this material arrangement now matters. So while some orientations are preferable from our previous knowledge on fields like dissimilar welding or DED graded materials, now we don't have that much freedom to reorientate the parts, so to make these transitions, and therefore new optimization routes need to be found for each material orientation, each arrangement of material to considerably reduce the intermixing region. However, this is not a magic laser still, and if we don't run a correct optimization, it still will or might lead to defects at the interface that can be caused by many factors, among them the formation of new faces or weak regions. While this solution can be incorporated in some of the systems that are currently available, multi-material systems that are currently available, no previous analysis on the influence of laser beam shaping on multi-material single tracks has been explored, which is crucial to understand the complex interactions taking place at the interface. Moreover, understanding this, how these thin interfaces are formed is key if we want to move on to bigger and more complex and intricate multi-material parts. So after this introduction, I will go over some of my latest results. We will focus on this latest proposed technology, which I explored for my combination of materials. And I will try to answer the question, can laser beam shaping help retain copper when depositing copper from zirconium onto Inconel 718 substrate? So for this study, we produce single tracks at which is a very well known and established method for determining the quality of the deposition. And we varied the scan speed, the laser power for 3 different laser modes at a fixed layer thickness of 60 microns that we determined in a previous study. That was the optimum for retaining the maximum amount of copper. After 60 microns, we don't experiment a huge retention on the amount of copper that we can deposit. We also fall into discontinuous regimes quite easily. So the single tracks were manufactured within the MIDI Plus system that we have here at RMIT, which is equipped with an N-Light laser, very fancy laser that can do the following. We can have access to the traditional or most standard laser source, which is a Gaussian laser that we see as mode 0 over here. But on top of that, we have the laser beam shaping technology that allows us to redistribute the energy density between the ring and the core, or Gaussian and the ring, up to 6 stages. So we will compare mode 6, mode 3, and mode 0, which determine as full Gaussian, almost full ring, and some intermediate state. And we will see how they can deal with the retention of copper, as well as the possible defects that we can encounter. So first we look at the processing windows for each laser source, and we've seen that as in previous single material studies with laser beam shaping, a much broader conduction regime can be achieved, as we see here. And one of the main things that we also can see is that the keyhole region that is typical from Gaussian is completely omitted for these 2 laser sources. This is great because it provides us a much broader window that we can work with. And yeah, that's mostly it from here. Following the processing windows, we look at the morphology, which I will briefly go over. So basically, we found out that the width, as expected, increased a little bit, had a positive trend with the energy density that we supplied, and they gained a little bit of a scatter the more energy that we supplied to the ring component of the laser. Most interestingly, when we look at the depth of our melt pulse, we found out that the mode 6 and mode 3, which are the non-Gaussian laser sources, produce a very shallow melt pulse, which was extremely interesting compared to the Gaussian, which grow very fast in depth. Which takes us to the next graph, which is the one from the aspect ratio that we usually evaluate. So the depth of a width ratio is usually a good reference from the transition from conduction regime to keyhole regime, around 0.8. And we observe that Gaussian crosses this line quite easily, falling above this line into keyhole mode. However, because of the signature shape of our non-Gaussian laser sources, we are able to remain under this line even at very high energy densities. We also studied the influence of the height for our track. This parameter is expected to be critical towards printing materials side by side in the future. And even though there are many benefits in laser beam shaping, up to now, layer height was definitely more inconclusive and less accurate than Gaussian, as we can see in the graph. So if we use electron dispersive spectroscopy to see the composition of the melt pulse, we can see some key differences between the 2 configurations obtained for the same processing parameters, but with different distribution of the energy source. The configuration obtained with Gaussian in the laser mode 0, we can see that it's a bit more elongated, typically from keyhole regime, and involving a lot of remelting of the substrate, starting here. However, if we look at the other one, the mode 6, we can see that it's very, very shallow, very low remelting, and a lot of copper content, very much closer to the original substrate start. So we decided to take a look at this copper concentration a bit more inside the melt pool and compare them for different laser modes and for different processing parameters to see which setup actually provided the best results. So if copper retention can be defined as the amount of copper present on top of the substrate, increasing the interaction volume actually will, or the depth, will lead to a lower copper retention. On the contrary, achieving low depth or lower remelting will lead to higher concentration of copper. And and this is what we are seeing with mode 6. This is key important because this is just single tracks, but when we do multiple single tracks together and then the next layer on top, the fact that we are remelting very little amount of the substrate will secure us that the transition is actually very fast. So we can take control on how big or small we can make this intermixing region. In this vein, the next graph shows us the average copper content retained inside the melt pool and the shape of the melt pool as a function of the energy provided with the laser source. It was clear to see that there was a great improvement in the copper retention when using laser beam shaping. One of the main reasons is associated to the rapid change to keyhole transition by the Gaussian laser source, which lead to a huge remelting of the substrate. Whereas for the laser beam shaping technologies, this transition is achieved much later, which starts to resemble keyhole mode here. But again, as I said in the previous slides, we didn't see an aspect ratio above 0.8. So can LBS help retain copper when depositing copper chromium zirconium onto Inconel 71 substrate? Well, the answer is yes, it is. But before wrapping it up, can we say anything about the cracking? How did LBS address this matter? What about, can we avoid it? Well, the answer is yes. No macro cracking was found. However, intergranular cracking was found at the heat affected zone. So very briefly, because I haven't included too much details on this, so I didn't know what the audience was, and I didn't want to stone this too much. I will just mention that we explored 3 cross sections for each configuration that we created, and we found intergranular cracking in the higher energy configurations for mode 0 and mode 3. However, mode C presented no cracks at all, which is great news. Nevertheless, this story is not over, because when we build bulk multi-material parts, we will introduce new problems, and therefore there is still work ahead. So for future work, I just want to very quickly go over some of the short-term goals that we're having, and this is translating the findings from this study that we're running on the single tracks onto controlling the interface at bulk multi-material samples. Also, we are planning to explore the solutions for other crack-free 3D arrangements. And lastly, we will evaluate the mechanical properties for the multi-material bonds that we are achieving from the different bonds that we show here in the schematic. And this is some of the latest results that we've obtained, just for you to have a very quick sneak peek. I want to conclude by giving a special thanks to the READY program, which has received funding from the European Union Horizon 2020 Research and Innovation Program, as well as giving a special thanks to my supervisors, Milan, Andre, Alex, vielen Dank, mein Supervisor von Fraunhofer IPT, Ingo Markelbasa, and the Additive Manufacturing pressing team, and the RMMF microscopy facility team for the scientific and technical support in this study. So these are my references, and I want to thank everybody here today for having your attention. It was a great pleasure, and Milan and I will be glad to answer any questions that you may have. Thank you.
Thank you very much, Jose. And in fact, we have several questions.
Great.
First one is this. So for specific industries like aerospace or automotive, can you highlight a target application where combining 2 metals would offer significant advantages over single material components?
So, I think that the aerospace industry and the space industry, I mean, they're looking at thermal management predominantly. So that's where the multi-material is going to play a major role in my view, Paolo. And they are already, working in this space. I think NASA is looking at multi-material alloys. and predominantly using the laser DD process, not necessarily powder bed process, but I think they are exploring powder bed as well.
Please, Milan.
As I said in my presentation, I mean this powder bed technology is very early stage, so it will take many years to basically develop the technology itself, and of course to develop a database of different alloys and look how they are, the mixing of the alloys and what happens at the interface. I'm just looking at some of the other questions. I mean, that's a challenge, and that's certainly something that Jose is looking at. It's that interface between the two different alloys, and can you eliminate, intermetallics? Can you eliminate cracking? So it's a great area for material scientists to explore. But in terms of technology and building parts, I think it's early days. But the opportunity is there, certainly.
There is one question related to your center, Milan, which is the Center for Additive Manufacturing's mission includes advancing multi-material additive manufacturing. What collaborative efforts with industry, other research centers, or standard organizations are underway to address gaps in process standardization or material property databases for multi-material laser powder bed fusion?
So at the moment, it's limited. I mean, we are members through Andrei Molotnikov, ASTM, and that standards community, basically. But there's really internally in Australia, we also members of our Standard Australia, but there's no real sort of major effort. There is a new cooperative research center that's just been awarded that involves industry and universities, and it's supported by the government. And one of the missions of that center is to look at standards and certification of AM parts. So that's where we'll be developing that along the way.
Yeah, also aligned with standards. The next question is specifically focusing on medical applications of multi-material additive manufacturing. And the question is, what regulatory or certification challenges are unique to multi-material structures compared to single alloy medical devices?
So, in my view, even single alloys, there are lots of challenges for medical implants. I mean, certification is an issue, and it takes a lot of time. You've got to go through animal studies. You've got to go through human studies before you get approval from US FDA, and in Australia it's TGA that approves this. So once that's been approved, fine, you can use it. And there are certainly companies like Stryker and others that are 3D printing components in single alloys. Now, as Professor Banerjee mentioned, I mean, multi-material is the next level up. And there's got to be a lot more studies, not just from the research side of things, but it's really from the testing side of things. So animal studies, human studies, before multi-materials can then be adopted as an implant and approved by these bodies, FDA, TGA, and other certification bodies.
Yeah. Could you elaborate on how multi-material laser powder bed fusion enables the fabrication of more complex and functional components compared to traditional single material approaches?
Yeah, is that for me or Jose? You can.
For both.
I think I can say this. So basically, when you make a component out of a single alloy, you're taking benefits. So the alloy is probably chosen based on the main requisites that you need for your component. However, with this new tool that we have available, where we can make discrete regions out of certain alloy, we can very much delegate some tasks to a very specific alloy that will excel at that task. So in the case that I described with the aerospace sector, I think there are very few unparalleled alloys that do better than copper in heat dissipation. We could use definitely gold, but we're not going to make a rocket out of gold. But we can definitely provide certain regions made of copper that will help dissipate the heat faster than, for example, an aluminum part will do. And still, we cannot. In some cases, copper won't be enough. A copper alloy will be enough. So you still need to provide the counterpart for the copper. So this is why, for example, nickel-based superalloys and copper-based alloys can marry together very nicely. But this is just one example. If you go for biomedical, maybe you could make use of a very what's the word? A cell-proliferating surface that is generated or by an alloy suited for biomedical uses, and maybe the inside part of the alloy of the implant can be made in something that is either, I'd say, more cheap, or something that is doesn't need to be so specific. So you can find almost uses in every industry. Energy can use it as well, and yeah, there are diverse examples. Yeah, I hope this answers your question.
What are the key challenges in achieving a strong interfacial bonding between different materials, and also how is your research addressing these issues?
Yes, so basically, at the moment, the bond between the two alloys that we are putting together is mostly defined by how much remelting we are achieving when we are depositing one alloy into the other, or when we are setting them up, when we are melting both of them side by side. It's related to how much we are remelting from each alloy when we are depositing it. However, there are additional variables playing on this. In my case, Incon 718 and the copper chromium zirconium actually get along quite nicely. There's some problems associated to the precipitation hardened alloy, the Incon 718. However, for some of the examples that I've shown with 316 copper, they are facing some other problems that are related to, for example, to copper corrosion cracking, and in some combinations which are, let's say, less advisable. For example, titanium and copper, you might encounter some other problems like the generation of very, very brittle phases that will, make your bonding really poor. So depending on which, let's say couple you choose, you will encounter different problems actually. But yeah, mostly on those, I would say those three are good things to keep in mind.
So we have many other questions. Let me pick the last one. What advancements in laser powder bed fusion technology are needed to make multi-material printing more industrially viable for high volume production?
Thanks, Paola. Yeah, look, the technology needs to be made more robust. Basically, that's the major challenge for the manufacturers of LPBF systems. And which approach is the best at the moment, I'm not really sure. I think time will tell whether the approach adopted by SLM Solution, for example, or the ones with Aconity. I think that the two main approaches, and one of those will dominate in coming years as they sort of spend more money on developing the technology. But it will take more time. I think we're looking at 5 years from now.
Prof. Milan Brandt and José, thank you very much. I know it's very late in Australia. We are almost in Saturday in Australia. Thank you so much, and we will collect all the other questions and send to you. And I would like also to invite all the participants, if you have additional questions, to send to both Prof. Milan Brandt and José Lozaras. Thank you very much.
Thank you, Paul.
Thanks, Paolo.
Now it's also a great pleasure to introduce the last speaker of this first webinar, Professor Shoufeng Yang. Professor Shoufeng was full professor and chair of additive manufacturing at University of Southampton in UK and KU Leuven in Belgium, before return to China and joined the Chongqing Institute of Green and Intelligence Technology, China's Academy of Science. Professor Yang is a visiting professor at the Singapore Center for 3D Printing, Nanyang Technological University in Singapore, Guangzhou University of Science and Technology, and Nanjing University of Science and Technology. He published more than 200 papers that received more than 70,000 citations. And his presentation today is titled Challenges in Powder Bed Multi-Material Additive Manufacturing, the Powder Bed Problem. Professor Shoufeng, the stage is yours. You are muted.
All right. Okay. Can you hear me now?
Yes.
Okay. Okay, thank you very much, Professor Paulo. Thank you for the invitation. Today, I'm going to talk about the challenges in powder bed-based multi-materials additive manufacturing, especially the powder bed problem. Well, I realized this problem about 20, 30 years ago when I started my research in additive manufacturing. And so my mainly focus area is we call the micromaterials dispensing technology. At the beginning, I started with the inkjet printing, then some extrusion as well. Then I more and more focus on powder bed based, especially dry powders.
Professor
I use this
Shoufeng,
technology.
sorry to interrupt. You are not sharing your screen.
Oh, right. Let me see. How can I share that? Yeah. Can you see that now? Right. Let me go.
Yes.
All right. Okay. Let me go back. It's okay now?
Yes. Now it's perfect.
Okay. Okay. I don't know. Maybe something wrong with my internet problem. You know, it's flash out to this Zoom meeting quite a few times before my presentation. Okay. My research area is mainly focused on micromaterial dispensing technology and use it for a few different areas like high throughput materials discovery, pharmaceutical production line filling, drug delivery and screening, and so on. Today I'm going to mainly talk about the multi-materials additive manufacturing. Right, I'm going to skip this because everybody knows what is the 3D printing. And if you look at the classification of the additive manufacturing, I'm more interested with this one because using raw materials to say either powder-based or solid-based or liquid-based or gas-based. So probably you see that most of the most important one are mainly focused on powder-based, especially the powder bed-based additive manufacturing. So one of the questions I've been always asked, why we are doing this multi-materials additive manufacturing, because one question you can see that how many materials we are using in our modern product. There's no exact answer, but in Cambridge Engineering Materials Selector, which is a very good database, there's about 4,000 materials for engineer. And this doesn't include the function materials such as doped material for semiconductor. I think myself is an engineer. So when we design the product, we are not only design the shape, but also we need to select the right materials. But how to select the right materials? Why are we using so many materials? Just simple, because single materials couldn't provide the multi and complex function that are required. And we always need compromise and joining and assembly. And for example, we need the copper for high thermal conductivity, aluminum, titanium and the fiber composite for lightweight, steel for anti-corrosion, and so on. That's why we have to select so many different materials. And there's argument that there's no perfect materials. Sure, there's a lot of material scientists are trying to improve the materials properties. But always, when you improve one performance, that means you sacrifice or compromise another property or performance. For example, we always know that if you increase the hardness of materials, typically you lose the toughness. And either we have to compromise or choose materials that we keep improve the material properties. But as that's more and more demanding and comprehensive, the multiple high performance of component product, material scientists and mechanical engineers are struggling to satisfy their customers or stakeholders. And sure, there's a lot of questions why we need to build this multi-material component. I give you a few examples. For example, this plastic mold and die casting tools. These tools quite expensive, and we want it to last forever. But we have to compromise a lot of properties. Especially the thermal conductivity normally is not very good. We have to wait for long cooling time, and the surface hardness is not ideal, so sometimes being wear out. If we can use different materials for different parts, like the conformal cooling channels, if we use harder materials for the surface, sure, we can improve the life of this mold. And if you look at a turbine engine, there's so many different temperature inside and so many different materials everywhere. And sure, we use 3D printing, we can put a lot of components together, especially like the figure underneath. And we have, a German company, I think it's a SM Solution or Concept Laser. They have successfully built more than 300 parts in one go, in this engine or the mainframe. But only one materials. But if you look at all of these components, you realize that all of the components actually are different materials. So you can build this structure but won't function. That is a challenge. Sure, like the earlier researcher mentioned that, like Rajarshi mentioned that bioimplant applications, I won't mention that again. And there's also some ideal materials or impossible materials, like the non-positive thermal expansion coefficient materials. Professor Sigmund have designed these materials more than 30 years ago, and nobody can achieve that. These materials, we know that every material have a positive thermal expansion coefficient. This is very bad if you want to need high precision machines. The temperature will change the dimension of the structure. Ideally, if you can have some materials which negative thermal expansion coefficient that can compensate this dimension change. So Sigmund is very clever. He mentioned this structure. So basically, you use two different materials with different thermal expansion coefficient and with a complex structure to get or zero or negative thermal expansion coefficient. But the structure is so complex and it's very three-dimensional multi-material structure, difficult to achieve. And a very hot topic, metamaterials as well. If you look at the structures, they're always using quite different materials. And when I got involved in this area about more than more than 25 years ago, my supervisor was Professor Julian Evans. He's a guy who invented a technology called direct inkjet printing technology, which is quite different with the binder jetting technology. So he print materials directly from the inkjet printing nozzles. Basically, he sacrificed his desktop inkjet printer, which was quite expensive, 30 years ago, and he reloaded the inkjet cartridge with different ceramic inks. And he built this functional gradient structure, about 30 years ago, and they were successful from the cornea to alumina, continued to change the composition. So then he got a pretty big EPS SRC grant. They said, oh, let's do some, function gradient materials with metals, with powder beds, based additive manufacturing. And he thought, I printed ceramics already using this direct inkjet printing technology. Why we can't change with, metal inks? Actually, this had happened already, but at that time, we realized that was impossible when I just started this project, because we know that in a powder bed based technology, the powder bed is so hot. We have to use a high power laser to melt the powders and to get thousands of degrees. And if you print any inks with solvents on it, you can imagine that would like, you spray some powder on your hot pans. So we have to think about how can we print with dry powders, just dry powders. And very luckily, but actually, unfortunately, it has happened about more than 20 years ago. The ActJet have commercialized this technology using direct inkjet printing. They have print ceramics and metals directly, and more interesting to print these multi-metals together. The technology is fantastic with such high resolution, and you can imagine that a real breakthrough of technology takes a very long time to be accepted or to be commercialized. From the started with the idea, it took about 20 years. But when you think about if you print a metals with this technology, you have to put in an oven. When the metals have different melting points, you have problem. So it's okay with ceramics, but with metals, it's a big challenge. And I'm sure there's a lot of research in the last couple of years. This quite early work using different powder feeding tank to feed different materials. You can see they can only change materials between layers, not inside layers. And also, Fraunhofer developed this technology by modifying a single materials technology by some suction unit and refill that. They print a very beautiful multi-material structure. If you look at the brush, the powder and the brush, you see the problem. All of the powders are mixed. And sure, they have thought about a lot of ways how to separate them, either using different sieves, different magnetic or different density. But I don't think, that is feasible, because you are talking about billions of particles, for some critical application, for example, in aerospace, you won't allow any contaminations in those mixed powders. And especially when the building volume are getting bigger and bigger, you talk about the meter size of powder bed. There's tons of the powder inside, and so expensive. You are talking about hundreds of thousands of pounds of powder in a tank. So how to avoid this cross contamination? And Professor Milan also mentioned about the aerosync technology, and it's a lovely piece of work on market now. But if you look at the details, they still have problem of cross-contamination. And when I was in KU Leuven, and this guy is from Aerosynth, and they went to my office and said, Professor Shoufeng Yang, I read all of your papers about multi-materials additive manufacturing. We got a lot of inspiration from that. So very good luck, they have done so well. And also Professor Lindley, from Manchester, they also use some suction and redispensing technology to build some multi-materials using some technology I developed, I will mention that earlier. And sure, Professor Rajesh and Milan also mentioned about the DED, you can use multi-nozzles to develop dispensing different powders, but we are struggling with the resolution or the high definition of the structures. Sure, there's a lot of different ways of thinking about how to do powder bed-based multi-materials, like even Xerox methods. And I reviewed all of these different ways, more than 15 years ago, and very challenging. There's so many different ways to do that. Sure, why this additive manufacturing hasn't been evolved into multi-materials additive manufacturing? If you look at the principle of the powder bed-based additive manufacturing, you see this is a problem because they use a ruler or scraper to spread the materials layer by layer. So you can't change the composition inside a layer. So the major challenge in multi-materials additive manufacturing is how to do with the powder bed. This is the first challenge. Sure, there's a lot of materials challenge as well. This is also some area we are working with. And especially my students, my colleagues are working on a lot of interface problem. And when I started with multi-materials, dry powder dispensing, I got stuck actually. I reviewed all the different ways on how to do that. I even look at all of the history of 2D printing. We thought, can we get some inspiration from the history? Because if you look at the 3D printing, the first 3D printer came from the number 7 lithography. We call it 3D lithography. And many 2D printing technology, which is both about publishing, not for material processing, actually have been evolving to 3D printing, but not all. Unfortunately, we can't find any clue from the history. And if you think about what is a multi-materials, if we compare with the 2D printing or publishing technology, that's kind of like a monocolor printing or color printing. You can use just 3 different colors to get so many different colors. So basically, you can use a few different materials to get so many different materials. That is our idea. And at that moment, luckily, I found that the Chinese ancients have given some ideas on that. I'm not quite sure if you have been you have visited Tibet, and this artwork from Tibetan monk, they call Tibetan monk sun painting. So a few monks could spend a few weeks to build such beautiful artwork using just dry sand. Then I thought, oh, they can manage so many different colors in one layer. If we can imagine each color is one materials, that is a multi-materials 3D printing. And sure, there's some similar things in North American Navajo Indians. And I was interested with how they do that. What kind of tool they have used. This is a simple tool they have used. I will show you a video actually how they do that. Let me see if you can see what happens. And because this work is so complex and so takes so many time to do that, it's not very usual to see that. So they use a very simple device called a chapel, and like a hopper, basically, when they stop some vibration, the flow of the powder stopped. When they start the vibration, the powder start to flow. It's like a valve to control the flow of powder. Sure, you can see, you can find a lot of valve to control the flow of gas, the flow of liquid. You know, you don't have see much valve to control powder flow, especially from a small region. So we can see this again, you know, how this control this smartly. And sure, we are scientists, we are engineers, we can't do this by hand. So I think, you know, how we do this using computer or using robotics to do that. So the right side is a simple hopper. I copy their metal coppers. Actually, it's very simple. It's just glass tube. I visit the chemicals shop, and you know, the glass blowers, they just find a piece of glass tube, then blow it, then draw it, then cut in the middle. They form a small copper like that, hopper like that. You can see that the powder just stuck there. They won't flow. And then I connect it to speaker and play some music to this small piece of the glass hopper. Then see what happened to and it's a pretty small glass tube. I'm just using powder, which is the same size as we use in additive manufacturing. Sure, actually, it's not easy to control with music because music has such complex frequency and amplitude. Just for demonstration, in a real time, we just use a single frequency and a single amplitude. But we change the frequency to see what we can control. Then there was a model to see how we control this flow rate and what happened inside the tube, inside this hopper. And we get the equation. If we know the frequency, if we know the particle size, we can predict the flow rate. And also, it's very interesting to see what happened when the vibration stops. Actually, it forms a dome structure inside the tube, stuck the tube. You know, it's like a procedural dome. You know, you don't have some cement to hold the bricks together. So it stays there. But when you have some earthquake, you break the dome. So like a vibration, we break the dome structure inside the small tube. And if we can have a lot of different tubes, each controlled at different flow rate, different frequency, different amplitude, we can have an orchestra to all play different music. We can even mix all these different powder together. And at the first time, the control is not very ideal. You can see I still can control the start and the stop, but you can see if you see closely, you see some match heads, at each dot, and also the resolution in the pore, typically it's millimeter size of resolution. And but I still try to manage to deposit a mixing of different materials like the copper and steel by online mixing. And actually, at that time, we even struggle with the laser. At that time, the laser is so expensive. There's no fiber laser, just a YAG laser. And I thought, we can't afford the laser. So can we do something without a laser? So we can deposit different materials. Why we can't deposit build materials or part materials and also mold materials layer by layer? So here is an example. We deposit stainless steel, which is a white part here, and also some black part with some graphite powder. So we deposit them together, layer by layer in a crucible. Then after that, we put in a furnace, and we got some nice part. Well, quite not that nice actually at that time, but we still struggle to get some three-dimensional parts. And sure, there's some problem with this interface problem, and we built some staircase. And so actually at that time I talked to the university when I was in Queen University, London. I said, oh, probably it's worth to patent that. He said, oh, do you have money to patent that? It's so expensive. So I thought, oh, forget about it. Let's just publish it. And recently, some companies actually are commercialized using this similar technology. And I realized that, the resolution is a big problem. If we can't get resolution higher and higher, that means, the cross-contamination won't give this technology go further. So because at the beginning, I used pretty low frequency of sound, you see the scattering of these materials when you have a pretty strong vibration. Then I realized, using ultrasound, you can get using a pretty higher frequency, but pretty low amplitude. Then you can control the resolution. At the time we can get pretty below, a few hundred micrometer of the resolution. And we can also dispense materials dot by dot. So like inkjet printing, we know that currently most of the inkjet printing are talking about drop on demand. We are talking about drop on demand. We need that materials, we just dispense that. If we don't need that, we stop. And the device is very simple, still the glass capillary, glass hopper with some, piezo, and try to use different, frequency of the wave and burst mode, and also shape to see what happened, and also try to put the piezo everywhere to see, how we can get better control, and try to find, what is the highest resolution without much error. That means every dispensing we got same dosage, because we can't put a balance, we can't put a balance inside a printer, right? We have to rely on this very reliable control, and also try different materials, try all different powder to see, can we do that? And luckily we can do many of them, but if the powder is very cohesive, we still have a challenge. But luckily for additive manufacturing, most powder are quite free-flowing. And we also developed some equation to predict that flow rate, and we found, some Bevel-Loader equation doesn't fit for such small scale, and we modify that. And the repeatability, as I mentioned, is critical. We can get pretty low as probably 1% of the relative standard deviation. That means error could be at a low as 1%, with about milligram of dispensing rate, or even microgram, depending on the nozzle size, depending on the particles, depending on the the property of the particles as well. And in the last almost 20 years, I keep improving the resolution or the control of the powder from this device, because I realized that one of the key performance is the resolution. So here, I show the picture of the high resolution we can achieve. We can achieve about 100 micrometer of track width with this dispensing technology, and quite difficult to achieve higher because particle size is pretty big. We are using 50 micrometer of the particle size. This case, we have to use about 10 micrometer of the particles. If you use still using smaller nozzles, but with big particle, we always got blocked. So that is a problem we are facing. But if we use smaller particles, we are also facing other problems, like it's more sticky or more compact density. But 100 micrometer is more or less enough for powder bed-based additive manufacturing, because we know the spore size of the laser is about 100 micrometer. So, and we also try to dispense different materials, try to dispense like something like a circuit. Here just a demo, we're using stainless steel, copper, and tungsten carbide, which was 3 different materials for the modes I mentioned earlier. and also try to do something called the structronics. Basically, you combine a structure with electronics inside. Sure, for electronics, you have to use some conductive things, and you can't print the chips. You have to insert them. And we also try to build the equipment, because without equipment, we can't go further either. So I built a platform with multiple nozzles, like the current inkjet printing technology. You basically, current inkjet printing technology, you use tens of thousands of nozzles together to give a mass production. But it's still quite challenging to do this with multiple powders at this stage. But sure, we have go step by step. And the interface problem, that is, especially when you facing a lot of different combinations with many different materials. Not all of the materials, they like each other. And we have explored quite a few, like copper and steel, copper and nickel, and different titanium, and other things. And I won't have time to report on further details, but probably later, because my team is working a lot in this area as well. Here is another example about the titanium. Titanium 6242 and TC4 together. And you can see we have built very nice interface, no any cracks, any defect in the interface. And also we investigate the width of the interface, because the width in the interface is quite important. We don't want a very small interface, a very narrow interface. Otherwise, the thermal expansion rate is quite different. So you can have a very big thermal stress. Actually, earlier when I look at all the questions, somebody actually asked this question. How you control the different thermal expansion rate for different material interface. So if you can control the width of this interface, that means you can control, you can minimize or get the stress of the interface smaller. And we also test different harness with, this nickel alloy, and also the tool steel H13. We can see, this very good, pretty good interface control. And also, I noticed that Joseph Beeman, who is the inventor of this powder bed-based technology, he started to do something about multi-materials as well, in solid free form fabrication a couple of years ago. He tried to dispense these different materials in one layer, but, sure, it doesn't seem quite smooth. But interesting thing is he mentioned quite a few publication as a reference, but 1/3 is from me. Okay, due to the time range, so I'm going to give you a short summary. A wide range of dry powder can be dispensed and controlled from different sizes of nozzles, and high precision of dispensing can be achieved, but this is still a small step in multi-materials. Like Professor Milan said, multi-materials, especially the powder bed, still in an early stage. We are facing a lot of challenges ahead, and there still needs a lot more to do in the material interface. And but good things, we can control the laser power with different materials. That is the advantage of this powder bed technology. And sorry, there's a few slides about in Chinese. This is talking about my team and also my institute. Try to advertise, try to hire some talent. And here is some of my group members. Most of them came from abroad, from KU Leuven, from UK, Singapore, Korean, Germany, and Australia as well. So and many of them are doing very well in material science. And this talking about the Chinese Academy of Science in Chongqing, and this is a structure, and we have a lot to we recruit a lot of PhDs, masters, and we have excellent facilities, especially very good swimming pools and very good dormitory and sports as well. So we welcome all the talent coming to us. And also, this campus, very beautiful and lovely. And also Chongqing is a very nice city, very good city for tourists. So thank you very much. Any questions?
Thank you very much, Professor Shoufeng. In fact, we have several questions. Let me start with the first one, and it is related to fatigue studies. And the question is there any fatigue study done on samples produced by multi-material printing? And is it possible to improve the fatigue behavior of parts using multi-material compared to single material?
Unfortunately, not yet. The fatigue problem is still actually a big problem for even single materials. So we haven't started to think about fatigue problem yet. We are still working on the interface to get the crack free, to get the defect free, and also try to build the equipment to control the composition with high resolution. So that is the main majority things we are focusing now. And sure, unfortunately, this is a future work we have to do.
Could you give us more details about recycling the powder after printing with multi-material printing?
That is thing we go back to why we talk about the resolution. Basically, if you can dispense these different materials at any location where you want, you don't need to worry about the recycle, because all of the support structure, you can use even sand. You don't care about, the recycling problem. So you can use any material because those support parts, they won't go inside your building parts. So you don't recycle these things. But sure, you can recycle the sand, but you don't, if you get very high resolution of this printing, you don't recycle the materials. You already use virgin materials. So that is what we are aiming to. But sure, not easy.
Yeah. How does your system ensure voxel level spatial control over material composition?
Pardon?
How does your system ensure voxel level spatial control over material composition, especially with different particle sizes, materials with different melting points, thermal properties?
Well, about if you talk about materials resolution or control that is a question not easy to say. We can control the powder dispense at the resolution about 100 micrometer, but when you using laser power to melt them together, as mentioned earlier by I think Professor Milan, right? They talk about even you can use a different laser profile to control the different mixing level at the interface. So there's a lot of interesting thing there, but we can't say, how well or what kind of resolution we can control the interface. But sure, if we can dispense many different composition at the interface, we probably can get better control as well. And also from the laser profile as well.
In your opinion, what are the biggest barriers to scaling this technology for industrial use?
Actually, the equipment. It depends on how we can get the equipment built. If we can't build the equipment, we can't go to the industry.
Yeah. Again, another one quite related. What is the feasibility, in your opinion, of utilizing or combining different materials such as metals, ceramics, polymers through your direct inkjet method or similar strategy?
That is a big question. It's not easy to answer. From material scientist point of view, it's almost impossible to combine metal and ceramics. Very, very few, successful examples in this area. But using this micro control of the composition might be possible. If you look at recently some literature, I can't remember who published that, at a small range, they combined ceramics, I think it's alumina or zirconia, zirconia, and some metals successfully together, but not in a big range, because for the powder-based laser additive manufacturing, it's not possible to get a crack-free or ceramics printed. It's so challenging to get even pure ceramics printed. If you can't even get one material printed, how you can combine them? For polymers, that's even more challenging because the melting point is so different. And so the selection is quite few. I have tried to combine metal, ceramics, and polymer together, but only in one case, which is solder materials, because the melting point of solder is about 200 degrees, which is pretty close to a melting point of nylon. So you are talking about, when the melting point of this material is so different, you are facing that when you melt one material, you also melt another, even solidified material, which has a low melting point. So that is a challenge. Talking about the the material interface, for metals and polymers, they have to physical bonding. You can never thought about, I shouldn't call never, because very difficult to sort out metallic bonding or materials level of bonding.
Mm-hmm. Also related to materials, what about the use of multi-material metal printing for 4D printing?
Pardon? For
4D printing. Materials for 4D printing. So materials.
4D printing. Right. Yeah, that's also a very interesting question, actually. There's so many research on 4D printing. I think one of the key issues in 4D printing is another dimension should be materials. The 3D is a dimension. Another dimension is materials. So if you can control the materials, and we can control another dimension, especially we will use some shape memory alloys, and you can control the shape of the structure more, probably more better in a 4D printing.
Again, we have several questions. I know that we are running out of time. Let me finish with this question. For multi-material structures with sharp interfaces, how does your dry powder technology ensure minimal mixing at the boundary?
No, we don't want minimum mixing. We want more mixing, because with minimum mixing, you have a very strong stress at the interface. You have more problem at failure at the interface. We want a metallic level of bonding at the interface. So, we have achieved higher mechanical strength at the interface, even, the strength of the interface is even higher than a single material. Like if we combine copper and steel together, the failure point we want is not in the interface, it's the copper side. So we want a strong bonding with, we don't want minimum mixing, but sure, when we facing some materials with difficult metallic bonding, we have to think about some third party of materials to bridge them together, to avoid, you can say that at this case, we have to avoid the mixing of this interface. So we need to find like high entropy of these materials. We have found something that's like each other.
Yeah, thank you very much, and what a great way to end the weekend and start the weekend. I would like to thank Professor Banerjee, Professor Milan Brandt, José Lozares, Professor Shoufeng Yang for your excellent presentations, and for allowing us to start this seminar series in such an excellent way. I would like to thank also all the participants, and we received more than 5,000 views. And for all of those working in this field, please consider the International Journal of Extreme Manufacturing as the ideal platform to publish your work. And by the way, together with Prof. Milan Brandt, Professor Lin Li, we have a special issue fully dedicated to multi-material metal printing. Finally, I would like to invite you all of you to attend the next webinar, which will take place in August. So stay tuned. Thank you very much, and have a nice weekend. Thank you.
Thank you.
Thank you very much.
Very much, Paulo.
Thank
you.
Paolo.
Bye-bye.
Bye-bye.
Thanks, Paolo.
Bye-bye. Yeah, Jose, it's Saturday. Sorry for taking you so long.
Very nice meeting.
It is fine. It is fine. It was again. It's a great pleasure. I began watching your seminar 2 years ago, and now I'm here. So yeah,
Oh, that's
full
great.
circle.
Yeah,
Great.
great.
Okay, nice
Thank you.
weekend.
Thank you very much. Bye-bye.
Nice weekend.
See you. Have a great
Bye.
weekend.